All right, welcome back to 2241. We're going over examples of quadric surfaces. And so let's go back in with problem number 6 here. Sketch this shape. All right, so I'm going to go ahead and classify this for us right away. We notice that we have x, y, and z all squared and on one side of the equation, and then 1 over there. So this is in standard form. And we have plus, plus, minus. We've got a minus. Remember, this is 1 minus, and so we have a 1 sheeted hyperboloid. And this was our sort of corset or crushed can looking shape. So it should look something sort of like this, maybe like a nuclear reactor. You're familiar with those, with what those look like. All right, so we'll put in our x, y, z axes. And so what does this thing look like? So which direction should it be opening? Well, maybe you'll make a guess that it's the z-axis, and it is. But why is that? Well, what happens when x and y are equal to 0? So let's see, if x equals 0, y equals 0, then we get negative z squared equal, or over 4 equal 1, and that implies that z squared equals negative 4. Uh-oh, this equation has no solutions in the real numbers, so along the z-axis, there can't be any part of the graph, right? In order to have solutions here, I would need x and y to be sufficiently large. They'd need to be large enough that I could add something to that side, or subtract something from that side and cancel out the negative there. All right. So now let's look at the form of this thing. We have x squared over 2 squared plus y squared over 1 squared minus z squared over 4. Z squared over 2 squared equals 1. And now we can draw our hyperbola. So if we set, I didn't label these. If we set x equal to 0 and then set y equal to 0, we'll be able to see what these shapes look a little bit better, or look like a little better. So x equals 0 gives me y squared over 1 squared minus z squared over 2 squared equal 1. And we already know that our paraboloid opens along the z-axis. And so we have this shape with sort of steep axes here, or like that. Then we can do the same thing over on this side. Open sort of steeply. And then move over. Okay. And so if you don't know this already, actually, the way that you can figure out how steep those lines need to be is that these lines should be asymptotic to the line y equal, not y equal, z equal 2y. Yes. Which means that if I draw those lines here, I'm going to draw them like that, then my parabola should get asymptotically close to them. Should treat them like an asymptote. Okay, so parabola gets close to those lines. All right, and then if y equals 0, what does it look like? Then we get x squared over 4 minus z squared over 4 equal 1, and 4 and 4 gives me 2 squared. So this is sort of a dilated unit parabola. 2 squared, 2 squared. And this guy should look something a little more like this in blue. So this is actually, maybe you might call this more like an elliptic one-sheeted hyperboloid. Because the cross sections here are ellipses. You draw out one of them maybe like this, should look like an ellipse. Okay, and then that is all of our shape, and we can go ahead and fill it in. In blue, we can draw in the rest of our grid lines, which should be ellipses that get larger and larger. Like this. And then same on the bottom. Our ellipses should look something like this. There we go. And we get the rest of our graph. A bit busy here. Oops, I want that red. And then the outline is going to look a little bit more like this. Not being super careful here, but that's the idea. Sort of a nuclear reactor shape. Maybe a hair curler. All right. Next problem. We have classify and sketch this shape. All right, so this is not in standard form. And we're going to want to rewrite it before we start drawing things and classifying. I do see a minus and everything is squared. So this might be, oh, and there's a constant term. So this might be some sort of a hyperboloid. Let's double check though. So we have 4x squared minus y squared plus 2z squared. And then we have plus 4. That's a bit odd. Well, minus 4 over here. And now we remember for standard form, we need that to be a 1. So we go ahead and divide by 4, or minus 4, and we get negative x squared plus y squared over 4 minus z squared over 2 equals 1. Okay, now let's rewrite that. Y squared over 2 squared minus x squared over 1 squared minus z squared over 2 squared equals 1. Okay, and so one way to help you decide how to draw these things is figure out where the circle or the ellipse is. Notice that these two terms are the same sign, so if I factor out a minus, this looks like the equation of an ellipse right there, an expression involved in the equation. So if y equals a specific value, I think it has to be at least 2, then we should be able to get an ellipse. More than 2, yeah. Okay, so this is going to be a 2-sheeted hyperboloid. And that is because it has these 2 minus signs here. So let's see what happens if y equals 0. So if y equals 0, we get x squared over 1 squared plus z squared over 2 squared equals negative 1. Uh-oh, that's an ellipse that doesn't exist, so y cannot be equal to 0. Right, well, what do we do then? Well, we set y maybe a little bit bigger. And let's choose something like y equal 2. Then we get 1 minus x squared over 1 squared plus z squared over 2 squared equals -1. And we can add this to the other side and add that to the other side to get 2 equal x squared over 1 squared plus z squared over 2 squared. And okay, that's not a 1, but if we divide it over, then we'll get the correct values here. The important point is that this is the shorter radius and this is the longer radius. Okay, so we should see ellipses in the xz plane, and they should get slightly larger as y gets larger. All right, now we have a bit of an idea of how this thing should look. We can try and draw it. A little bit weird in standard form, but I think we can do it. Let me start drawing. So we have a hyperbola here, and it actually opens in both directions, and then the same thing on the other side. Let's just fix that up a little bit, make it look a little bit more hyperbolic, I guess is the word. Sort of like this. Okay. Okay, it's a little hard to draw this. It's not really participating with me very well. Okay, good enough. That should do. Then I'm just going to go ahead and fill this in. So we should have some ellipses here. Really make this super elliptical. But the graph should look something like that. And cross sections along the y-axis should be ellipses. Okay, and so here's our two-sheeted hyperboloid. Here we have x, y, z. All right, you can fill in the grid lines for that one if you like. Next, classify the surface given by this other equation not in standard form. Okay, so we need to rewrite this in standard form somehow. Note that this is different because now we have terms that do not have degree 2. So we should group, we've seen this trick before, all of the x terms together. Say, all right, what am I going to add to make this a perfect square? We're going to complete our squares. And then we have, right, no other y terms here, only the z squared term and the y term. So y, maybe we'll bring that to the other side of the equation. And then z is on its own right there. So we have 2z squared plus 10 equals y. Okay, and what should I add and subtract here? Well, I should add and subtract whatever makes it a square. You do your completing the square method, it turns out that's a 9. So I need to add 9 on both sides. And I get x minus 3 squared plus 2z squared plus 1 equals y. So this is an elliptic paraboloid. It's got a y to the 1 term. And it is shifted along the x-axis by 3 and scaled along the z-axis by 2, and also shifted along the y-axis by 1. So this is a little trickier. We'll draw this very carefully now. 1, 2, 3. Right? And just to remind ourselves, we're doing an elliptic paraboloid. That has been shifted. X, Y, Z. Okay. So let's find its vertex. The vertex should be, all right, this number, and then whatever I've subtracted from z, which is 0, and then whatever I've subtracted from y, or added to, the other side is 1. So our vertex is going to be at the point 3, 1, 0. So x minus 3, z minus nothing, and y minus 1. I bring the 1 over to the other side. Okay, so let's see, 3 along the x, 1 along the y right there, and then it should open in the y direction. So I have sort of a graph that should be moved actually a little bit. We need to move the x and y axes a little bit upward. That'll make things a little better, hopefully. Yeah, there we go. Okay, so now I can draw in that vertex point. 3, 1, right about there. And then draw in my paraboloid, which is steeper in the z direction than the x direction. So my graph is going to look something like this. So steep z, and then not so steep x. And there, that's a little better. Okay, and then I get to fill in my outline. It's going to look a little elliptical there. And the rest of these should go like this. And all right, that's sort of what our shape looks like now. These weird lines here. Okay, that's an elliptic paraboloid, and my drawing's not great on that one, but hopefully you get the idea. All right, and then last but not least, reduce, classify, and sketch the graph of this equation. So same trick, just a little bit more complicated. Figured we'd get 2 examples of this in. We have 4y squared plus z squared minus x minus 16y minus 4z plus 20 equals 0. And we want to collect our like terms. So we've got y's together and we've got z's together this time. And it looks like x is on its own with no square. So let's bring the x to that side, and then we'll collect the z terms with each other and the y terms with each other. That should give us 4y squared minus 4 or minus 16y plus something. And plus negative z squared minus 4z plus something plus 20 equals x. All right, and so this is a little bit more work that we have to do. This needs to be reduced somewhat further. Notice we have 4, 16, and then minuses all through here. So let's go ahead and do some factoring. I'll factor out a 4 from this, and we get y squared minus 4y. Now I need to figure out what to add here. And then minus z squared plus 4z plus something here. Plus 20 equals x. Okay. So we need to add and subtract, if I remember correctly. This should be a 4 minus 4, and this is going to be plus 4 minus 4 as well. So we should have 4 times y squared minus 4y plus 4, and then minus 4 times 4 minus z squared plus 4z plus 4 minus negative 4 plus 20, and we have x at the end. All right, almost there. We have 4 times y minus 2 squared minus z plus 2 squared. And then we have 16 here, positive 4, and 20. So we have 20 minus 12 is 8. Plus 8 in the x direction. Okay, which is still fairly large. And so this is our reduced quadric equation. All right, so what's going on here? Well, we have what is this? So this is a paraboloid, I believe. Yeah, it's a paraboloid along the x direction, and we have y and z. So z is subtracted, it's the minus 1, and y is the positive 1. And then we have our vertex, which is going to look like 2 minus 2, 8. Vertex. I know it feels weird to say the vertex of a hyperboloid, but it is more or less a vertex. Same idea. It's where the thing is centered around. So 8, 2, minus 2. This will be a little bit harder to draw, but I'll try. Let's see what we get here. So our x-axis to be pretty darn big here, because our vertex is at 8. So let's say 1, 2, 3, 4, 5, 6, 7, 8. And then 2 in the y direction, 1, 2, 2 in the z direction, minus 2 in the z direction, 1, 2. Right about there is where our axis, our vertex should go. That's our vertex, 8, 2, minus 2. Okay, we got x, y, and z. And our hyperbolic paraboloid is going to open along the x direction. So I need to move this a little further up. And we can get our first parabola. Remember, y was the positive direction, so it should open this way. And it should be kind of steep, actually. Y had a coefficient of 4. And then in the z direction, we had just a -1 coefficient, so it should open sort of fat like that. And then we can go ahead and fill in the rest by just sort of filling in the dots. And that didn't do what I wanted it to. A little bit more like that, and there we go. So there's the rest of our hyperboloid. So this is hyperbolic paraboloid. This is our hyperbolic paraboloid. All right, so more or less the same principles as when you first learned how to do these sorts of things apply. They are just a little bit more tricky to deal with. You have more variables and thus more room for error. Okay. So those are our examples for the quadric surfaces section. Make sure you get lots of practice drawing these things and identifying them from the equations. It'll be very helpful later on.